Hi everyone and welcome to this video about similar triangles. Before we begin the content of this video, please remember to like and subscribe if you enjoyed it. And remember, you can always drop a comment down below if you had any questions about the video or you would like me to make a video on another topic. To understand similar triangles, we first have to understand what mathematically similar means. These are shapes with the exact same proportions and shape. They might, however, be different in size. However, we want a more rigorous way of thinking about mathematically similar triangles. One way to think about what I've just said is that if we take a shape and enlarge it to produce a second larger mathematically similar shape, each part of the original shape will correspond to a particular part of the new shape. Let me show you an example of that. Let's say I take my quadrilateral on the left, and what I'm going to do is make it bigger. We can see that the left angle, the top angle, and the bottom angle, as well as the right-hand angle, so all of the angles of the shape, correspond to a new angle in the larger shape. The side lengths remain in proportion. The ratio of the left top side to the right top side should be the same as the original smaller shape's ratio between those two sides. Mathematically similar objects can be in 2 dimensions or in 3 dimensions. However, for this video, we're just going to be focusing on 2-dimensional triangles. There are 3 facts that we must know about similar triangles. The first is that corresponding angles are equal. Let me explain what I mean by this. So we said before that this bottom left angle will correspond to a new angle in the larger shape. And because I've just taken this shape, I've not changed the orientation and just dragged it larger, we know that it must correspond to this angle in the bottom left of the large triangle. So corresponding angles being equal, these 2 angles must be the same size. The same with the top angle, and the same with the bottom right angle. We can test if 2 triangles are similar by looking at the angles. If the first shape has the exact 3 same angles as the second shape, then they're going to be similar. The next fact that we need to know is that the internal ratios of sides are the same for both triangles. The internal ratio of a triangle means the ratio of the sides within the triangle itself. So for the left-hand triangle, I could make the ratio AB to BC. So I've taken this length here and put it in a ratio with the bottom length there. We might write that as a fraction, AB over BC. Now this ratio should be the exact same if I take the corresponding sides in the large triangle and create the same ratio. So what I'm going to do is I'm going to take the 2 same corresponding sides and create a ratio with them, DE over EF. And these 2 fractions, these 2 ratios will be the exact same thing. Of course, we could do this with any sides of the triangle. So for example, AB and AC will be the same as DE and DF placed into ratios like this. The final fact is that the ratios of corresponding sides are going to be equal. And what I mean by corresponding sides is, for example, AB and DE. We can see that AB has just been stretched, elongated to create the larger triangle, and that side in the larger triangle is DE. Okay, so the corresponding sides are AB and DE, AC and DF, BC and EF. So that's what I mean by corresponding sides, and the ratios of corresponding sides are all equal. Writing this out would look like AB over DE equals AC over DF equals BC over EF. In practice, what this means is that we're going to multiply the lengths of each of the sides of the smaller triangle by the same number to get the side length of the larger triangle. As an example, let's say that DE is twice the length of AB. So this side here is twice the length of this side here. That means to go from AB to DE, I would times by 2, or the fraction AB to DE would be 1 over 2. Now I said that to go from the small triangle to the large triangle, we'd multiply by 2 each time. So that means that AC divided by DF would create the same fraction 1 over 2. So we can see that no matter which pair of corresponding sides I choose, that fraction will always be the same. That ratio will always be the same. To check for similar triangles, we just need to check one of these facts. So for two triangles, if one of these facts is correct, that means those two triangles are similar triangles. Let's take a look at an example question together. Looking at these two triangles, I first need to test that they're similar. Well, in this case, I don't actually have to because the question tells me that the two are similar, but let's do it just for practice. We can see that this bottom left angle is the same in both triangles. This top angle is the same in both triangles. So the remaining angle must also be the same because the sum of all of the angles in each triangle needs to add up to 180 degrees. So now that we've established that the triangles are similar, let's make sure that we understand the orientation of both of them so we can work out which side corresponds to which. We can see that in fact the orientation of both triangles is the same, with this angle pointing upwards and this angle pointing to the bottom left. That means that x will correspond to y, 4 will correspond to 12, and 16.5 will correspond to this length CB. The question asks us to calculate the length of BC, so let's mark that on the diagram. As I said before, BC corresponds to this length, which is 16.5 centimeters long. Now, which of the rules will we need to work out BC? Well done if you said the ratio of corresponding sides are equal. That's the one that we're going to need to relate together the two triangles. What we can do is create a fraction or a ratio between the small and the large triangle using the two lengths that correspond to each other with a numerical value given. That fraction is going to be 4 over 12, and we know that that must be equal to this small length and its corresponding larger length in a ratio. So let's write BC, as we don't know this length, divided by 16.5. Now I can rearrange my equation, timesing both sides by 16.5, and placing that into my calculator, I can work out the length of BC, which is 11 over 2 centimeters. The next part of the question is to write down an expression for y in terms of x. So we know that x and y are going to be related in a ratio that is the same as the ratio that we previously calculated. Remember, the ratio of corresponding sides are equal, so the ratio of x to y will be the same as the ratio of AB to PQ. Let's write that down. So x over y is going to be equal to 4 over 12. Now we want an expression for y in terms of x, so we need to rearrange y to be the subject of the equation. Let's times both sides by y, and we can divide both sides by 4 over 12. 4 over 12 simplifies to 1 over 3, so in fact we can just multiply both sides by 3. And that is the final answer for this question. Let's have a look at this last example question together. This is a very common type of question that we might find in an exam. So while it might not look like we have two similar triangles, it's our job to be able to spot them. Now, as in the previous question, we're going to look at the angles to determine if these triangles are similar. With BE and CD being parallel, we can draw some constructions on this diagram to find out if some of the angles are the same as each other or not. So what we're going to do is draw on these parallel lines, and we're going to pick CBA first. Now, if you know corresponding angles, you might notice that this angle and this angle must be the same, as BE and CD are the parallel lines in this case. You might remember corresponding angles as F angles, but hopefully you can see that they must be the same. If you didn't quite understand that step, please leave a comment down below and I can help answer any questions you might have. We can do something similar on the other side. So again, BE and CD are parallel, and we have this line DEA running through those parallel lines. So again, we can see that these angles here must be corresponding angles and thus the same. So looking at the smaller triangle at the top, we're just missing one angle there, and that is BAE. We can also see for the big triangle CDA that the top angle is shared. So we've proven that all three angles are the same in both triangles, and thus they must be similar. Once we know that the triangles are similar, we can use the other two rules to our advantage. The first thing to determine is which sides in fact correspond to each other. The easiest pair to spot is BE and CD, these two lines at the bottom of their respective triangles. The other two sides are slightly harder to spot. It's in fact AE and AD that correspond to each other. Let's bear that in mind when we're setting up our ratios. So first let's find the common ratio shared between the corresponding sides in the smaller triangle and the bigger triangle. To do that, we're going to use 1.5 and 6. And we know that this ratio is the same for each set of corresponding sides, so we know that that is equal to the unknown side AE and the corresponding side in the larger triangle AD, which is 5. So multiplying both sides by 5, we can work out the final answer, which is 5/4 centimeters. Thank you for watching this video. I'm glad you've made it all the way to the end. If you have any questions about the video, remember you can leave them down in the comment section below. Please like and subscribe if you enjoyed it, and I will see you in the next video.